Okay, thank you very much. And first of all, thanks to organizers for the opportunity to speak at this very nice, great, and very stimulating meeting dedicated to academician Sakharov. So what I want to try to convey to you in the next half an hour is my view on analytic infinite derivative gravity theories, which I'm trying to develop for quite an amount of recent time, let's say almost for 1.5 decades. And here I will be talking about two major points, in my opinion, related to quantizing any theory, about propagator and about unitarity. And all of this is based on recent papers in collaboration with Sravan Kumar, Alexei Starobinsky, Anna Tokareva, and some work in progress, which is on the way. And I'm really thankful to Frank because he already introduced a lot of stuff. And I really decided just to skip at least one slide, and I just will go to the point. And the point is here. This is an action which I really encourage people to pay attention to, because I really think it's worth paying attention to. Why? Because it is, in my opinion, very promising action to study gravity, and there is a great hope that it may lead to something like quantum gravity. And I will try to explain why I am so optimistic about what is written here. So first of all, what is written here? It's Einstein action, a little bit of lambda if it is. I don't know whether it is or not, but let's, for generality, it should be here. And the three terms which are quadratic in curvatures. And for curvatures, I choose scalar curvature R, a second rank tensor, which is a little bit not Ricci tensor, but it's traceless part, and Weil tensor. It's a matter of choice what I do here, Weil, Riemann, or whatever. Weil is convenient, it's 0 on conformally flat backgrounds. And this answer was obtained in these two papers in collaboration with Tirto Biswas and Anupam Mazumdar. And what is exactly the answer for? The answer is exactly to the following question. Imagine that we start with such an action which contains any function of curvatures and any function O of covariant derivatives. As long as I build everything upon curvatures and derivatives, I don't break diffeomorphism invariance, I live and remain in geometry, I'm quite good to go. As long as dependence of these functions is analytic with respect to curvatures and derivatives, I restore infrared limit, which I hope to be GR limit. And starting from this general analytic gravity, as we named it, I want to ask the following question: what is the most generic term which I need to analyze linear perturbations around maximally symmetric spacetime? And a linear perturbation essentially means that I will derive propagator. And maximally symmetric spacetime essentially means Minkowski or de Sitter or anti-de Sitter, and nothing more, at least as long as the dimension is greater than 2. As such, the question was put precisely. I want to see what are the terms out of all this mess which contribute to quadratic variation of the action, or equivalently to linear perturbations of equations of motion. And the previous slide was exactly the answer. Only these terms correspond. And these terms comprise of GR, which is trivial to understand, but quadratic terms, it is essential, have they are sandwiched by functions which are often named form factors, and these form factors are analytic functions of D'Alembertian. And these f small x, these are constant coefficients. So technically speaking, this is Taylor series at 0. So these functions are analytic at 0, and this is because I started with something which is analytic at 0. I definitely do not touch infrared modifications of gravity. Just because I don't touch them, it doesn't mean that they're excluded by some generic principle. No, I just want to talk about ultraviolet. So talking ultraviolet for the rest of the talk, I just explained briefly that I need such an action, and this all I need. And this definitely, even though it's a little bit longer written, it's much more transparent than this unspecified set of messy summations and products. And this is one intermediate result. We were able to deduce the second variation of the action with respect to transverse and traces part of the metric. And this is the answer. This answer is very important to what I will be saying because it explains clearly why, for example, Koshelev could not avoid a ghost, and why you will never be able to avoid a ghost as long as you keep finite number of derivatives here, because this is what you get. This is canonical box minus R over 6 factor in the kinetic term, and this is P of box is a term, is a factor, is an operator which arises thanks to all of these R squared corrections. So this unity is like it would be in GR. This constant term which depends on R bar is a background curvature of my maximally symmetric spacetime. This green part is what would it be R squared, local R squared. Yeah. And this is what would you have a Weil square term with FW function. But you see, this is an important observation here. Whatever FW is, even if it is 1, you always have some extra box here. And if it is 1, like Koshelev suggested to use, we immediately have that P of box, like it is in the stellar case, is something like 1 plus box. 1 here, some constant here, and box here, which is immediately a second box dependent, the Lambertian dependent factor here in our kinetic term, which, following the Ostrogradsky statement, is a way to get a ghost, and there is no way around. Yeah. For scalars, the picture is fairly similar, and yeah, there are also some terms, but here picture is a little bit more promising because actually we know that scalar part, scalar perturbation of the metric can generate us something sensible like scalaron. So in principle here we can expect that something happens, and I really don't want to pay attention to all of this because all of this is talking about scalars, and I present it for completeness, but I really want to continue about tensors. Why? Because I hope that tensors is what I need from gravity first. This is my graviton. Of course, I need scalaron for a lot of things, but graviton is my primary point of attention. Actually, when we go to this, and we abbreviate it often like analytic infinite derivative gravity, actually, if we look to this action closer, and if we just study this quadratic in curvature action, in principle, we can find out a lot more. And if we, for a moment, forget the story that we obtained it as a description of a maximally symmetric spacetime around some messy gravity theory, then in principle, we will find a lot. And we can find, for example, Newtonian potential, which is regular at 0. We can find a lot of solutions, and in particular, we can find solutions which satisfy this condition box R equal R1R, which essentially means R squared, local R squared equation of motion, and as such, we can incorporate all possible solutions found in local R squared gravity, and Starobinsky solution in particular. And Starobinsky inflation becomes an exact solution of our model, exact upon a little bit of tuning of form factors, but this tuning is really really does require only fixing form factors in 2 points, so not too much. Also, in some previous papers, we were able to find some stable ghost-free bouncing scenarios in the framework of this action. So here I want to come to a statement that generically, given the previous explanation, I generically like this action. And I want to convey the idea that this quadratic and curvature analytic infinite derivative action may be already enough to start attacking quantum gravity. We don't know yet whether it's possible or not, but we definitely should give it a try. And this is what we could do. We start with propagator. And the observation which was made once is the following. The physical propagator around Friedman-Robertson-Walker background can be computed. And this is a little bit more generic than it could be around Minkowski space. But even if it is Minkowski space, no one stops us from doing 1 plus 3 decomposition. This looks like much more physical, because then we will extract really 3-dimensional Hij tensor and describe really physical 2 polarizations of graviton. We can find out that in principle in this ADM 1 plus 3 decomposition, these propagators for scalar part, for Bardeen potential, and for tensor with respect to 3-dimensional symmetry group look like this first and second line respectively. And you see what is fantastic from this observation is that now it doesn't seem like these 2 form factors which looked before like independent functions, f box and fw, of box are really independent. Because you will have to really connect them in order to avoid problems with description of your scalar degree of freedom, because you have to tackle somehow the denominator in this formula, because finally it should not produce you something strange. Moreover, you see here that whatever corresponds to a tensor entirely depends only on function fw and not on function f. And as a generic idea, we don't want extra degrees of freedom. And as I just asked Frank about this, I really don't want any extra degree of freedom, neither with real nor with complex poles. I just don't want any extra pole on the complex plane. This essentially means that it imposes some restrictions on my function fw and f. The restrictions come from the following understanding. This is what is going on. We can have some scalar field theory with propagator defined by box minus m squared, and this is what we have in a canonical scalar field theory or whatever field theory. This is my field phi, and this is kinetic operator box minus m squared, and being inverted, it is a propagator. And if for some reason we have 2 factors, like here in the bottom formula on this slide, then it looks like it's not great, because this will correspond effectively to 2 fields, and one of them will be a ghost. And we know pretty much that there is no way around out of this. Yeah. Technically, we can continue to any finite order in D'Alembertians, and no way to eradicate ghosts. The trick is somehow suggested and motivated by string theory consideration is to say that if we have extra derivatives, we have them in terms of a factor which should be nothing but exponent of entire function. Because this is the only mathematical construction which does not produce zeros. Exponent of entire function doesn't have zero on a complex plane, and as such, being inverted, it doesn't generate a pole on the whole complex plane. And in principle, the simplest entire functions are polynomials, and the simplest polynomial is just a box. It's not the best, and I will explain a little bit later why. But definitely, if someone wants to see something more specific, he would definitely start with a polynomial, because nothing simpler you can substitute here. At least for computational reasons, you will start with exponent of box or box squared or something like that. Also, I want to mention that even though I pronounced that this is somehow motivated by string theory, and especially string field theory, and even though I like generically string approach to quantum gravity, I want to emphasize that just before I have shown you that generically higher derivatives arise kind of automatically without any initial string consideration. Just any gravity theory would dictate me to boil down consideration of a propagator around, for example, Minkowski space to something with higher derivatives. And now coming back to my propagator story, I just want to say that coming back to this gravity consideration, this is what I want to see, that my propagator for scalars, kinetic operator for scalars, is of the form like written here, like D'Alembertian minus some mass squared, and then exponent of entire function. Propagator for tensor modes is again D'Alembertian multiplied by exponent of entire function. If I try to satisfy these two relations, then I will immediately see that I can find what is fw, and then I also can immediately see what is my function f of box. It is definitely and clearly related to fw of box, and from this moment I become a little bit more happy, because now I see that I really decreased the freedom in choice of my parameters 2 times, because before I was thinking really for a long time, and it was written in many of papers that I need 2 functions to define my action. Now I see that it looks like I need 1 function, fw, and then the second follows, and there is no way around. And this is some progress in my opinion. But what I want to ask next, what in general should I do with such theories which have such factor in my kinetic operator? And of course, I'm not crazy enough to go to consider quantum gravity from the very beginning, because I even not sure how to consider quantum scalar field theory here. And we started to do some steps, and these steps were done in collaboration with Anna Tokarev recently. And here is our, let's say, very short explanation, very short rephrasing of our paper, in which we tried to see what happens indeed if we consider such a scalar field theory, which looks like okay, normal field theory with this red factor, which is some function of D'Alembertian. Just as a matter of notation, I want to say that for this particular consideration, I will keep plus minus signature opposite to what was used before, just because all this paper was written in this signature following quantum field theory books. And you see, this doesn't seem to be like an easy task, because surely if this is some exponent of entire function, which is okay from the point of view of not having pole, this definitely introduces essential singularity at infinity. These tricks like f at 0 equal f at m squared equal 1 just guarantee the IR limit. It's nothing special about this. And of course, also it's sure, since we now introduced such a huge freedom in our theory, we definitely will gonna to use it to calm down all the divergences. But definitely we have to say what to do with essential singularity, and in particular, how to work with it upon integration in Feynman graphs, because definitely whatever was named like weak rotation in quantum field theory book would never work here. Why? Because this big arc along which you have to rotate your contour of integration, would you follow standard prescription, would exactly go through essential singularity. Not nice. It's not nice at all. And this is demonstration why. Because if you define an amplitude, you have to compute integral like this. And if you define amplitude in Euclidean signature, you have to compute integral like that. And usually you do it by this change of variable k0, zero component of momentum goes to its imaginary counterpart. And this is exactly amplitude for a tadpole. The trick of weak rotation in a local field theory usually works, thanks to the fact that integral over this big arc is zero. This is how this integral looks like here. And it's definitely not zero unless you really fine-tune your form factor. And this fine-tuning is way beyond anything required by conditions that you don't want ghost. So it's something extra. But still, as you see here, you can do something about your form factor to fine-tune it. The problem is that this, what is written here, would be a fine-tuning only for one graph, for a tadpole. And it will not work for any other graph. And even you can imagine fine-tuning for next and next and next graph, you should understand and expect infinitely many tunings for your form factor, which doesn't seem like an acceptable way. And then we go to, so this was just explanation why we should not use weak rotation, but then the question is what to use, because finally we kind of expect that we live in a Minkowski signature, and even if we use Euclidean signature, it should be just computational convenience or whatever. And the answer comes upon study of this fish diagram, following the paper by Pius and Sen, who also studied the same question some time ago, and their resolution to the puzzle was in the following proposal, which they didn't end up with explicit computation in their paper, but their idea was, in short, as such that in principle, whatever you have to compute here, all the loop integrals here inside, you have to do in Euclidean signature. And then whatever you get afterwards, you have to analytically continue to Minkowski values. And this, for a local theory, exactly coincides with a trick named weak rotation. This, however, may or may not give you something sensible here. And the task which we put in front of us was to check what happens exactly for the fish graph and what would be the amplitude, and whether it does or not satisfy, for example, optical theorem. And in short, we had to compute this amplitude corresponding to this graph. And surely it is not possible, let's say, to compute it for a generic form factor. And as a matter of first try, we did it for just exponent of box. It is not incredibly difficult, and we came to an answer. Answer is a bit long, but it has two nice properties which we really liked. So first of all, it is totally analytic, and it does satisfy optical theorem, because the imaginary part of amplitude which comes from this piece, because you have to, in the full answer, multiply by I, so we have to single out this real minus p cube. The imaginary part of your amplitude indeed satisfy optical theorem statement, so it's already something. But what was even more important to see explicitly is that when alpha goes to 0, and we essentially restore local limit, because essentially form factor goes to a constant, we exactly restore the answer for logarithmic divergence as it should be in the cutoff regularization. To our opinion, this is extreme check that the proposal works, because it does give us optical theorem first and local limit second. And of course, then we can restore the whole answer, which would look like this. But it's not end of the story, because what we have observed, it's not the best answer which you can restore here. And exponent of box, exactly this operator, is not the is not something giving you all right, just because you will really see problems in ultraviolet regime and stuff like this. So you have to think whether you can do something for another type of form factor, and maybe from here find out some restrictions or conditions on your form factor. And this is what we also could do analytically. For this particular graph, we could do computation for any arbitrary even form factor which is even with replace to the Lambertian to minus the Lambertian. This is the answer. It looks a little bit long. What is surprising here that it is written explicitly in terms of simple integrals. It depends only on your form factor here, only on these two form factors here. In principle, you can even perform integration over x of this product of three Bessel functions. The answer is simple. It's just not very much illuminating, let's say like this, but still simple. But what is really interesting, what we have observed here, yeah, first of all, of course, we again see that imaginary part which would be verified and checked for optical theorem statements is here, and it works. This is great. But what else which is really interesting here, that this last term gives the main contribution to our answer, and as long as we require that form factor is some integrable function, this piece gives us universal contribution of 1 over p squared decay at infinity. No matter what you have here, this will be in the term in the first line, whatever complicated looks like, it will be subleading correction. This is an observation which we made considering nowadays quite generic form factor. And in principle, we have reason to even say that this is maybe enough, because when you have really form factor even with respect to replacement box to minus box or key squared to minus key squared, technically speaking, you have form factor which can be equally well integrable along both real and imaginary axes. So there is a reason to consider such class of form factors. And maybe it's already interesting observation on its own that we have a universal contribution 1 over p squared here. And moreover, if we take some particular form factor, for example, like exponent of minus p to the fourth, or this form factor which is motivated by study of Terry-Tomboulis, then we will really see that the model remains weakly coupled. And here, yeah, I don't have any constants and everything put to precise values, just because this is exactly how we did numeric computations of this amplitude fixing parameters. And this convinces us that in principle, theory can be made unitary. When I say made unitary, I mean exactly that we have a clear procedure how to tackle infinite derivative theory to have it to satisfy optical theorem. And this, we believe, is a good step towards naming the theory unitary. It's not a final proof, of course. You have to consider a lot of things. And people spend really decades or maybe their lives to prove unitarity in certain cases. But this already a step forward compared to what was done before. And another point which I wanted to touch here, which we observed in another paper with Anna, considering the same story about delocalizing some model, is very much related to what I was asking to Frank about complex poles and generically what to expect from such theories and how to tackle them, especially given that sometimes we don't just need perturbative quantization around some vacuum, but rather we need something more like effective potential, for example, or stuff like that. And what I want to outline here is a study which we did related to Higgs inflation model as a toy model to play with delocalization and some analytic infinite derivative modification. This was the action that we were studying, which contained Einstein gravity and scalar field and some potential. And even though it's supposed to be a model of Higgs inflation, I'm not going to details of this. It's first of all, it was a lot said about Higgs inflation even today. Moreover, I want to emphasize another point related to exactly presence of non-local infinite derivative form factor here. And the point is like this. As I explained before, you see, we can make the theory ghost-free. And we can even speak about propagator, loops, and we even can tell something how unitarity is maintained. But here there is a question which we observed when we were looking carefully at this model, that when we say that the model is ghost-free, technically speaking, we only speak about some states considered about some vacuum, around some vacuum. And here, for sure, in this particular Lagrangian, which seems like some massless excitation corresponding to the Lambertian and some form factor which we want to be exponent of entire function, yes, it can be done a ghost-free model. And to require that it is ghost-free model, we have to demand that second derivative of the potential in the vacuum is 0. This follows from this equation, because equation of motion is like this. Sorry, there is a misprint here. I had to put here phi, the field phi on which this operator acts. So technically, it should be field phi here. And you see, would it be the second variation of the potential, second derivative of the potential 0, then indeed this operator box and then exponent of entire function of box is operator which has only one possible solution, operator which is technically equivalent to second order equation because it's equivalent to just acting by the Lambertian. Exponent of entire function doesn't matter. But if this is not 0, but if it is a constant, then it's not clear what to do with all of that, because first of all, just from a mathematical point of view, this will correspond to infinitely many excitations. And moreover, only one of them will be real, and all other will have exactly complex poles. And we were thinking how to treat all of that, and is it possible to treat all of that? And we found quite nice observation related to this particular issue. And at this moment, we really want to thank Professor Rubakov for asking us proper question during one of the talk. And observation boils down to the following, that indeed, we can generate a lot of excitations if this right-hand side is not 0. This we can, no question. But the crucial point is, even if they are ghosts, and half of them will be ghosts, and you can really reparameterize this all field such that you will clearly see that part of them are okay and part of them are ghosts. The question is whether we can really do something about these fields such that all their classical solutions are decaying. So you see, we are not anymore asking questions whether these are states or whether they are ghosts. Yes, they will be, and they will be states, and they will be ghosts. And even though they appear not around a vacuum, they can appear somewhere in the intermediate stage of evolution. And we accept that they are not so nice, but we ask the question whether they grow or decay during their own evolution. And if they grow, not so good. If they decay, it's already something. Question, can we really do that these fields, these extra excitations, do really decay? And the answer is, yeah, we can. Answer here is the following. If we consider something around the Sitter background for simplicity, then the answer is the following. Whatever masses of excitations we obtain from this equation, they should obey the following relation. A relation is very clear. It says that imaginary part of mass squared and all of this being squared should be less than 9 times a real part of mass squared multiplied by h squared, whereas h is a Hubble rate of our de Sitter space. If we can do this, we are good to go. If we cannot, not great. But the point is that in order to do it, we have to adjust the shape of the form factor, which we from now on consider as an extra and quite important restriction on our form factor, but what is the most important, not impossible. There is no theorem in the complex analysis which would prohibit us to do so. It doesn't mean that we can easily write form factor which satisfy all of this, even though we can, at least in form of some contour integrals on the complex plane. But the point is that we can do it. Such form factors exist, and the matter of this observation, the end point of this particular observation is the following. We must satisfy this, and we can do it adjusting the shape of our form factor. And this follows from the fact that these masses are mainly governed by the shape of the form factor, while something also is governed by the shape of the scalar field potential. This can be totally left generic in a sense that it's okay just to fix form factor here. So having said this, let me come to my conclusion, because I believe I'm very close to end of time for my talk.
It's already exhausted.
Okay, so let me just conclude. It's the last one. So I'm talking about class of analytic infinite derivative theories. And I have in mind that this can be a promising starting point to construct UV complete and unitary gravity. And these models do have connection with string field theory, which I never emphasized, but I keep in mind that it exists. And in this theory, we have a lot of nice properties, which I didn't talk deeply here. But some of them I will still mention. It's embedding of Starobinsky inflation and a lot of observation from here discussed by Sravan in the morning. It is finiteness of Newtonian potential as kind of generic statement for any analytic form factor, which suppress loop integrals at infinity. And in general, this method helps regularizing different theories. And we do provide some explicit computations showing nice properties of the propagator. And one of them, which I showed here, is that we really can restrict everything, reduce everything to just one form factor in all the action. And the last is that we have clear statement about how to maintain unitarity and how to maintain optical theorem in this class of theories, which gives us hope that we are at least on the right first step towards considering this type of models. Thank you very much.
Okay, thank you. And the first question from Richard Woodard, please.
Okay, thank you for this nice talk. Let's see, I had two questions. One is, what does the Cauchy problem look like for your model? And the second one is, if I may have misunderstood, but I thought I understood you of saying that you get exponentially falling solutions, but not exponentially growing solutions. And if that's true, I'm just puzzled. Is this theory not time symmetric? And if so, how do I see that from the action?
Well, when I was, I believe when you're asking about growing or decaying solutions, you're asking about this consideration, how to contain these modes. In this particular case, I was considering it coupled to gravity in a, well, not really minimal, but in some way coupled to gravity. I cannot name it minimal because I have a lot of G here. And yes, as long as we were considering here the de Sitter stuff, yeah, it is possible thanks to de Sitter properties, to this presence of H, having that both modes of these solutions are decaying. It doesn't mean that other modes related to real, to the solution corresponding to
What
the real
breaks the
pole
time symmetry? If I just run the theory backwards, why does it not give exponential growing solution?
If you run time back, there will be growing modes, but we want to define this as initial condition, let's say at the infinite past, and then go forward. We want to say that this would be good for our in our vacuum from which we start, yeah, from which I'm not really gonna too much backward, even though I can consider this and think what would happen would I invert the time. This is indeed very interesting question, but for the time being, we will consider it as this at this stage. We will consider this evolution at classical level, yeah, with time going forward.
Okay, what does the Cauchy problem look like?
The Cauchy problem is a much more involved story, but it is like this. If you define the Cauchy problem, in a vacuum, especially in a vacuum in which you really can guarantee that this right-hand side is 0, then exponent of entire function of whatever operator does not contribute to Cauchy problem. So essentially you reduce your problem to Cauchy problem of the Lambertian. And if for some chance you want or get here non-zero on the right hand side, or just consider more complicated operator generically, then yeah, generically you boil down to Cauchy problem with infinitely many initial conditions, which is not proper Cauchy problem, I would say. So you have to work in order to constrain your vacuum such that in your vacuum, at least, you can put the Cauchy problem.
Okay, thank you.
Okay, the next question from Tim Morris, please.
Hi, Alexei. Thank you for a lovely talk. At the end, you mentioned the possibility that you can make this thing UV complete by, I assume, by making sure that sigma grows with momenta.
Yes.
So that the propagator then decays exponentially. Yes. Yeah, but then once you consider gravity, these growing terms will lead to exponentially growing interactions. You know, once you start to perturb in the graviton and work out, say, the one graviton vertex, that will grow exponentially in such a way as to kill the benefit that you get from the exponential decay of the propagator. And this is the well-known problem that higher derivative regularization doesn't work at one loop.
Yeah, this is why I specifically mentioned, but didn't elaborate on this function, which I now show here at the bottom, form factor, which was for a while developed by and discussed by Terry Tumboulis. You are not obliged to have exponential decay of your propagator because you're not obliged to have form factors like this exponent to minus p squared or minus p to the fourth or whatever. You can consider somewhat much more complicated, really. And this is a precise, explicit example what can be whatever written in the exponent here. You can check it. It is still an entire function, and incomplete gamma function plus log is indeed an entire function, but exponent of it is an example of construction which decays at infinity polynomially. And practically this one decays at 1 to p to the fourth, thanks to this p to the fourth factor, okay? So technically, you are not obliged to have exponential decay in this class of models, and you can easily go to polynomial decay of your propagator with all other prerequisites kept intact. So this may.
But polynomial decay, at least naively, polynomial decay is not enough. I mean, if you add a polynomial of higher derivatives to the action, you don't regularize the theory. That's the problem of higher derivative regularization.
What do you mean? If I have polynomial, I will not regularize?
Well, because if you add covariant high derivatives,
Yes.
you know, some polynomial covariant high derivatives,
Yes.
generate new vertices which grow in momenta in a precisely a way to cancel any benefit that you've gained from the propagator.
No, but here maybe I a little bit missing something. But yeah, I mean, surely in one loop, one will cancel each other, and no way you will still compute one loop like you did in GR. It's okay, and someone maybe is.
It'll be divergent, so it's not UV complete, and that leads on to my next question, which is I don't see how you preserve these forms once you start to take into account renormalization.
This is, of course, an important question, and so yes, of course, one should check that it is possible. We neither have explicit computation to show that it is possible to preserve, nor we have no-go statement that it cannot be preserved. My expectation is that it will introduce some new, maybe very heavy in terms of computation. I mean, some restrictions on form factor, but I don't deem it as impossible. Even though, yes, it's an important question, of course, but related to I was kind of always taught by a book of Slavnov and Fadeev, which told me that polynomial high derivative regularization is totally enough to regularize at least young mills.
Slavnov, in their papers, they also have to introduce a gauge invariant Pauli-Villers to fix the one loop.
No, one loop is extra question. One loop is okay, because you see here, one loop story is trivial in a sense, because you need to compute only one loop correction with 2 3-point vertices to the propagator, and all the rest should come from Slavnov-Taylor identities. In a sense, I hope that, I mean, this is exactly what Koshelev was doing. He was computing one graph and then restoring everything from it. And as long as I don't break diffeomorphism invariance, which I don't, I hope to enjoy the same joy doing all of that. But of course, this is very important to check it out explicitly. What happens upon one loop computation, counter terms, and stuff like that? This is an open question for sure.
Yeah, cheers.
Okay, the next question from Irina Yefimova, please.
Okay. Oh, thank you. Thank you, Alexei, for nice, concentrate talk. Better to say that I have some remark. Here you discuss some model where you have very complicated dependence on derivative, and you assume that you are dealing with so-called analytical dependence on high derivative. In fact, I'm not quite sure that such general stuff can work, but definitely what can we believe is a string theory. Everybody believes that in string theory we can do weak rotation. But the question is, can this rotation survive under level truncation? What was presented here is some kind of model inspired by level truncation in string field theory. So if we do, I cannot say that in any truncation, we will not get problem. But definitely, maybe we have somehow a little bit modified level truncation. In fact, the true situation can be in some respect simple and in some respect more complicated. Because if you do a real truncation in unitarity theory, then we cannot say that all derivatives come from the exponential form, for example, like is presented in this last transparencies, that everything comes as exponential with minus second derivative. In fact, the life is a more complicated, but still, since we are started from good theory, unfortunately, we have a proof this is a good theory only in flat background. We don't know how it looks like in non-flat background. We can believe that it's really possible. So my general comments may be during consideration of such time of problem, we have a little bit change the level truncation during the calculations. That's all what I want to say. Okay, thank you.
This I agree that in principle.
Yes,
In principle,
when we started with
as I
you many
understand,
years ago, more than 15 years ago, to do
yeah.
all these calculations, for example, with the consideration for Q, for bosonic string, it's okay in first example for tachyonic. But if you consider more complicated model like superstring models, then in this case, the situation is the form of this effective action is more complicated, but people know that only superstring is okay. For bosonic string is unstable model, so maybe it not provide us the good example. But nevertheless, we have to work in this direction and see what happens. Okay. Thank you.
Yeah. So in some sense, I think maybe even better to invert a little bit your comment in a sense that maybe considering how weak rotation should be modified, it's possible to see what would be consistent level truncation scheme which would preserve weak rotation in string field theory language, which may be an important question, because technically you are saying that level truncation may violate weak rotation, which we observe here.
Well, exactly.
And then
exactly.
you are saying that generically, because strings should be unitary theory in which we, so in principle, this is in this language somehow related to what is written in this particular paragraph. And it's not our invention, it's invention by Pius and Sen to say that we need to modify the prescription how to compute integrals. And this indeed may result in somewhat rethinking how level truncation scheme and string field theory works. But definitely, since it is a remark, I'm not supposed to really answer, and I definitely cannot answer right away what can this mean for string field theory. But it's very curious way to think about this.
Okay, I agree. But we have work more.
Yeah, sure.
Okay, so thank you again, Alexei. And now we can go to the next talk.